So I want to do the second part of section 3.6, and here we're going to be dealing with inequalities with rational functions. And it's going to be the same idea, except we have one extra element, and that's going to be vertical asymptotes. And what's significant about vertical asymptotes is they can be objects where you see a change in sign as we go from left to right. Now, like x-intercepts, this doesn't have to happen. You can have x-intercepts where a function contacts the x-axis, but then sort of bounces right off. So even though it's 0 here, positive function, positive function. The same is actually true of vertical asymptotes. Your x-axis, here's a vertical asymptote. And there are functions that behave like this. And a function, for example, 1 over x squared. So they don't always lead to a sign change. For this one, positive f of x, or positive y. But sometimes they can. We can have negative values for f of x, and then on the other side of the vertical asymptote, we can have positive values. So similar to x-intercepts, these are places in our graph where we could see a change in sign. So when we're interested about when a function is positive or negative, when it's greater than 0 or less than 0, we're not just going to look for x-intercepts when we work with rational functions. We're also going to look for vertical asymptotes. So taking a look at this one, this function, call this intercept A, say this is at x equals b, and this is intercept c. So you want to see where f of x is greater than 0. Well, that's where the function is above the x-axis. And that's going to be from A and then to the left of A. Let's suppose this keeps going off to positive infinity. So along this x-axis here, to the left of A, this just keeps rising. Now, from A to B, B is where you have the vertical asymptote, say hash mark B here. Our function's below the x-axis, so it's not going to work. But between B and C, it's above the x-axis again. And that's it for f of x greater than 0. Now, if you look for less than 0, this is where f of x is below the x-axis. So from A to B. And also from C to, well, not really from C. C is where it's equal to 0. But to the right of C. So to the left of A, f of x was greater than 0. To the right of C, it's less than 0. And so there we go. Now, oftentimes, we won't have a graph to work with. So what we need to do is come up with test points. And the same idea with polynomials, with test points, where if the test point, say here, the test point's positive, then all the values of f of x are also going to be positive. Now, why is that? Well, what the test point really is indicating is what all the points are doing. All the points in this interval are above the x-axis. And the reason is they can only dip below the x-axis if they cross over it. In other words, they have to pass through x-intercepts. You can't switch signs unless you pass through x-intercepts. There's a little caveat to that. I'll get to that in a second. There is a situation where you can. So because these points, this part of the curve, will never cross the x-axis again. Again, we're assuming these are the only x-intercepts. Because they're the only x-intercepts, there's not going to be an x-intercept out here where our curve can cross over it or pass through it. So that means these points here, if they're up here, they're going to stay up here. And that's how we know, just realizing what one of these points is, well, positive or negative, that tells us all of them will identify as positive. Same thing here. If we find out that the test point here is negative, because there are no x-intercepts between A and B, all these points have to be negative. Now, the other place, again, where you can switch sign is at the vertical asymptote. And you can go from negative, and then if we pop over, it's now positive. So this is the extra bit we need to keep an eye on. Passing through the intercepts can allow you to change sign, but also passing over, going from one side of a vertical asymptote to another, that could also allow you to change sign. So when we're working with these, we're going to be using test points between the x-intercepts and between the intercepts and vertical asymptotes, and also on the far sides. So the general procedure is this. We're going to set f of x equal to 0. And this will give us the x-intercepts. But in addition to this, we'll set q of x equal to 0 in, remember we describe f of x as a rational function as p of x over q of x. And factors in q of x that can't cancel with p of x, they don't simplify away, those will become vertical asymptotes. Those are the VAs. So to give an example, if we have, say, x plus 1, let's go x plus 3. So this is our q of x, and we can see it's going to be 0 for x is negative 3 and for x is negative 5. Now, that would suggest that negative 3 causes division by 0 and negative 5 causes division by 0, except it absolutely says that's the case. So the difference, though, and this seems like, well, golly, I mean, there must be a vertical asymptote at negative 3 and a vertical asymptote at negative 5. But that's not how this works out. Because x plus 3 will cancel, what we'll get is a hole. We get a hole at x is minus 3. When the factor that goes to 0 or could cause a division by 0 cancels out, it simplifies away. We get a hole with this factor. But the one that doesn't simplify away, that becomes a vertical asymptote. So we're going to look for these vertical asymptotes. We're going to look for these x-intercepts. And then finally, test points, or what I call TPs. So for test points, we'll place them between x-intercepts and vertical asymptotes. Because this is where something can change the sign. Now, a hole doesn't necessarily mean this is where the function changes sign. They don't have to exist where the function is going to be crossing over the x-axis, for example. They don't have to do that. And there is the possibility, though, you could have a hole where you have an x-intercept, or where you usually would, depending on this function you're working on. So in that case, a hole could be a, well, that'd be a change of sign. But they're generally not indicative of changes of sign. That typically happens at your x-intercepts and your vertical asymptotes. So we're not going to go out of our way to look for holes. Now, the other place we'll look for test points, far sides. All right. So let's look at this one. So let's say we have something like this. Well, what we want to do is look for x-intercepts. And so we start out that equal to 0. And again, what we're going to be doing is ultimately we're setting this top part equal to 0. So we could multiply, but just to show where that comes from, if you were to multiply both sides by x plus 3, that would cancel. You'll get x minus 4 is equal to 0, or x equals 4. So that means we're going to have some x-intercept at 4, 0. Now for vertical asymptotes. Well, this isn't going to cancel with anything up here. So this will be a factor that could become 0 that's going to stay there. And I want to find out where this occurs. So we're going to find a vertical asymptote at x equals -3. So these are the places that we could expect a change in sign. So if we take our x-axis, -3, +4. So we have a vertical asymptote at -3 and an x-intercept at +4. So we need some test points. Again, I say go with something kind of easy. 0. That's not too hard to calculate. And then on the outsides, the far sides, I'd say 10, -10. Arithmetic with 10, it tends to be easy, can be. And then let's see what's going on with these test points. So we have a 0 here. Then we have a vertical asymptote. So this is where the function is equal to 0. So f of x, let's do f of negative 10. So we get positive 2. So that means the interval containing negative 10, and that interval is going to be to the left of this vertical asymptote. It's going to be positive. So do we see a sign change at 0? Now this is the 0 on the x-axis, while this is the value of the function at 4. F of 4 is equal to 0. So let's find out. And then negative divided by positive is negative. So we get negative. So we're going to get something like that. And so we do get a sign change as we go from this side of the vertical asymptote to that side. One more, f of 10. We get 6/13, which also is positive. So this is what we've got. So what conclusions can we draw? Well, first off, where this is greater than 0, it's to the left of negative 3. So it's going to be over here. And then it's also going to be to the right of 4. And since we don't have an equal to here, we don't include the x-intercept here. And we would never include the vertical asymptote. That's never going to be included. Again, this is a place that the function can't have a value. So we'll have 4 positive infinity. And that's going to be your answer. Now let's take a look at another one. Now let's say we have this. So we have this less than or equal to 0. Well, again, we want to see where this is equal to 0. You can multiply both sides by x plus 1. And what you'll get, you set this equal to 0. Here, I'll go through this step again. But really what's going to happen is we're going to take this top part and equate it to 0. And so this will give us x-intercepts. X is negative 3, and x is 2. And again, the reason being is the zero product principle. This times this is 0. So when you multiply two things together, that product is 0 only if one or both of those things are 0 themselves. So this right here, this is 0 when x is minus 3. This here is 0 when x is 2. So that's how we get our x-intercepts. Let's make a note up there. Finally, the vertical asymptote. Well, this isn't going to cancel with anything up there. So find out where q of x is equal to 0. At x equals -1. So at -3 and 2, we have our x-intercepts. And at -1, we have a vertical asymptote. So the function has a value of 0 here, value of 0 here, and then the vertical asymptote just right there. So we need test points. So let's say we choose something, again, easy to use in calculations, test point of 0. We'll do it this way. This here we could use -2, and out here we could use, say, -10, and here we could use 10. So we have test points between the x-intercepts and the vertical asymptote, and then on the far side. So let's compute the value of these test points. Now, -10. So the key thing is going to be the sign. Now we got 7 times 12 is 84. Negative times negative is positive. So we get positive 84 divided by -9. So positive divided by negative is, well, negative. So you get -84/9. So that means to the left of -3, our function is going to be negative. All right, so let's see what's going on between -3 and -1. Oh, we'll use -2 as our test point. And this will come out to +4. So we're going to have positive between -3 and the vertical asymptote at -1. So -1 to 2, we're going to use the test point of 0. And this will be -6. So we get a negative answer. So we have a negative there. And then finally, 10. So we get 13, 2, 11. And so 26 divided by 11, well, that's going to be 26 11ths. We'll just leave it at that. But the point is it's positive. So the function here is positive. So again, we haven't graphed this function. We don't know exactly what it looks like, but we do know where it's going to be above the x-axis and where it's below the x-axis. So what's going on? Well, our conclusions, it could be equal to 0. So we want to include intercepts when we have them. Again, we can't include this -1 because vertical asymptote function doesn't have a value at that location. So we want less than or equal to 0. So we want the negative intervals. Well, the function's negative to the right, I'm sorry, the left of -3, and it's equal to 0 at -3. So we're going to get this. We'll include -3, again, because the function's 0 there, and it's okay for the function to be equal to 0. That's what we want in this problem. Now here, it's also going to be negative from -1 to 2. Now, we don't include the vertical asymptote. Again, the function doesn't have a value there. So -1, comma, and we do include 2, though, because we could be equal to 0. The function is 0 at 2. And that's our answer. So that's it. If any questions, let me know. Other than that, have a wonderful day.